Hi,
Hey,
Keone.
Keone. Hey, Keone. Hope you feel better. He's probably sick. That's probably why he's home. He's sick, so he's probably got the flu or something. Do you feel better, Keone? All right. So we talked about gravitational potential energy. We talked about kinetic energy. Today we're going to talk about elastic energy, which is a strange form of chemical energy, not where energy is not stored in the in the potential energy of the bonds, but in the vibrations of the molecules and their intermolecular forces. So we start with Hooke's law. Hooke's law is pretty cool, and it says if a spring obeys Hooke's law, then the force of expansion or compression is related to its stiffness and the extension from equilibrium. Should have grabbed. You know, I need to go to spring. I need to get a spring. Show what I mean. It's my giant bin of springs. We got some compression springs in here, and I got some expansion springs in here. And we're actually going to investigate Hooke's law in the lab. But let's look at the easy ones first. Okay, so this is an expansion spring. This is equilibrium. There's nothing pulling on it. If I put a mass on it, it's going to extend down equal to the weight of the mass times, or equal to the stiffness of the spring times its extension. So if you have a spring with a spring constant, that's the K, of 1, and you put a 10 Newton mass on it, it's going to extend 0.1. Okay, does that make sense?
Yeah.
So the stiffness of the spring times expansion is the force. And it's, again, this is one of those things. Okay, so let me take it aside. This is one of those formulas. I mean, there's going to be a lot of them. This is one of those formulas that is written so you can remember it, but it's not like the cause and effect is wrong. So what it should be is the extension of a spring is equal to the force you apply divided by its stiffness. Does that make sense? So that's what it's really saying is if you apply a certain weight on this or a certain force on this, it will extend a distance based on its stiffness. So if you have a very high stiffness, it'll extend less with the same amount of force. If you have a low stiffness, it'll extend more with a given force. So far, so good? And we also say, this is super important, we also say the spring obeys Hooke's law. So later on, we're going to learn about Ohm's law. We'll say it's an ohmic material or not ohmic material. But when we're looking at spring, we say the spring obeys Hooke's law, meaning it obeys this formula. Does a spring always obey Hooke's law? No. So I got a million of these things. It was for a project that I put together almost 20 years ago. We got a ton of these things. So this is a spring that can be both compressed and extended. Okay, so it obeys Hooke's law right now. If I push it with a certain amount of force, it'll extend, and then if I pull it with a certain amount of force, it'll extend the exact same way. It'll basically have the same springiness whether I push it or pull it. However, if I put too much force, it's bigger. The spring no longer obeys Hooke's law. Okay, so if you look at the formula of Hooke's law as F equals negative kx, it looks a lot like y equals mx. Where if you apply a certain force, it'll extend a certain distance. It goes the other way?
Well, that's like the original form.
Yeah. Okay. So it'll basically, it'll obey Hooke's law, right? Meaning, if you apply a small force, it's going to apply it'll extend a little bit, right? Apply a small force, it'll extend a little bit. A little bit more force, it'll extend a little bit. A little more force, it'll extend a little bit. Eventually, it falls off and breaks. So it doesn't matter how much force you apply, it's no longer going to obey Hooke's law. So we say the spring obeys Hooke's law until it doesn't. So like the extension spring, they'd be like, yep, it obeys Hooke's. Oh, here's a mass kit. I can hang my mass kit from it, and it obeys Hooke's law. Need a bigger mass. Right? Now here's the important thing. The distance is always measured from the point of equilibrium. Right now, there is zero mass, therefore zero force, therefore no extension. We ignore the entire mass of the spring until you get to college. And then if I put a mass on it, the distance that extends from the equilibrium point is the x. Does that make sense? So you always measure from the same point on the spring. I got these cute little mass kits. Isn't this cool? This is for an AP physics lab that we used to do. It was really fun. All right, so if you remember, the work done when you apply the work done that increases potential energy is force times distance, right? So if I'm storing energy in a spring, I take that force, which is given through that Hooke's law, and the distance over which it is extended, and I get the formula, work equals negative kx times d. Because this is F right here. Can you see how that's F?
Yeah.
So the formula becomes the work, or the change in energy that is installed into a spring, is kx squared. But it needs one more term. And that is the amount of force that is applied on a spring increases as the extension increases. So you need to use an average. Simplest way to do an average between starting and ending, divide by 2. So simplest way, you realize that if you want to find the starting point and ending point and find the average in between, you just add them together and divide by 2. So there's one more term, you need to divide by 2. So the energy stored in a spring is 1/2 kx squared.
That formula works for now later.
Yeah. It's very similar to the formula that we use for kinetic energy.
1/2 squared, 1/2 mv squared, 1/2 kx squared.
Mm-hmm. It's all about averaging two variables. And if you chose to go further in your education in physics, you will learn there's a little bit of calculus we can rub into it to make it even more precise. All right, so take a look at this. How much would a spring with a constant of 200, by the way, I keep forgetting to change the units. Do you know what the units of a spring constant are?
Can't say.
Well, remember, context clues. In math and science, units always have to cancel. Because not only when there's an equal sign, not only the numbers have to equal, the units have to equal too. So if our unit is, our formula is F equals kx, x is a distance measured in meters. F is a force measured in newtons. So not only do the numbers have to cancel or be equal, the units do too. So the unit of K is the Newton per meter. Which again, if you rearrange the equation, you can be like, okay, I'm going to rearrange the equation and I'm going to turn F equals Kx into K equals F over X, Newton per meter. So you have a spring with a constant of 200 Newton per meter. You're going to compress it 2 kilograms, like in the diagram. Here. So you have a spring with a mass of 200. It's compressed when a 2 kilogram mass is dropped onto it from 2 meters above. This is asking two things. The first thing it's asking is how much, when it bounced all the way down and it came back and settled out, how much would it have extended from its equilibrium point? The other thing it's asking is how far would it go all the way down? Because you know, if you drop something on a spring, like if I took one of these springs, if I drop something on it, it would go squish, up, down, and then eventually settle out. So it's asking two things. First thing's the easiest. Where would it be when it settled out? Figure that out.
So a constant of 200. It's not like 2.00. It's just 200.
It's 200, yeah, 200 point Newton meters. Hang in there, Amy. Do you need a fruit snack? Do you need a fruit snack?
I just had one sure.
Fruit snack has sugar.
Let's see, I'm pretty sure.
What did you guys get?
Pause. For which one?
How far down did it go in the first?
It's the moss, not that artificial welch.
When you drop it, how far down it
Yeah.
0.091.
That's not what I got. But
That's what I got.
Probably.
I got points.
Don't ask me because I probably did it wrong. So.
Let's
So you got the same thing I
I
did.
did.
Yeah,
I
what
got
did you do?
0.2.
Okay. Oh wait,
I mean,
did you multiply it by
technically-
10 and not 9.81? Yeah, that's why.
How'd you get
Okay, so x equals 0.
Mhm.
You're going to drop it. This is a, say, 2 kilogram. This is a 2 kilogram mass. Okay, and it's dropped from 2 meters above.
Yep.
So I'm just going to use the bottom of the thing just to make it easy. So it's going to drop 2.0 meters.
Oh wait.
So can we say that the block loses potential energy?
Yes.
And can we say that the spring gains potential energy?
Yes.
So the MGH of the block equals the 1/2 kx squared of the block, of the spring. So this is the PE grav of the block equals the PE spring. By the way, you can write elastic if you want, but I'm just going to write spring because it's easier to write. Mass of the block, 2.0. Can we just use 10?
Yeah,
Yeah.
I really like using that.
G is 10
Makes
and
everything
H
so
is
easy.
2. So we have a total potential energy of
Stuff, everything is so easy.
40 joules. Yeah. For the whiteboard, we're going to use 10. And the calculator, we use 9.81. And then 1/2 times 200 times x squared. So that looks like 100. And dividing it, so that looks like 0.4 equals x squared. Are we good so far? So x equals square root of 0.4. I'm thinking like 0.28.
0.63.
0.63. Oh, the other direction, right. So 0.63 meters. So it's going to go,
I did not.
here, I'll draw this one. It's going to go right about here. This is 2, this is 1, this is 6. Okay. So it's going to go right down here. So it's going to drop 0.63 meters.
Wait,
Okay.
isn't that just the potential energy of the spring?
Yes.
Is that, do you not have to plug it into like work equals force times distance or anything?
It's taken into account the 1/2 kx squared.
Yeah.
All right. Next, there's 2 things calculated here. Because it goes, boing, but then it pushes back. And when it stops moving, the spring is pushing up only against the weight of the block. Right? So then we can do another equation, this time in red, where we're going to say the FG of the block equals the F of the spring, which we know to be negative K. Pretend that's okay, negative Kx. So far, so good. So, what's the block weight?
2 times 10.
20 newtons?
Yeah.
And we said that the K is 200 times X. So the X is how much when the spring returns?
0.11.
0.1. 0.1 meters. So it only goes here at delta x equals 0.
So the
Mhm.
the 0.63 is how much it does like initially once it first dropped.
Yeah, because when it's moving, it's going to go crunch, and it's going to have to absorb all of that energy. All the potential energy the block is going to have to be absorbed into the spring. But then the spring is going to push back, and it's going to push back with a force equaling kx. And the force it pushes back when there's no more motion, remember no more motion means the up vector equals the down vector? So it goes down, boom, and then it's compressed way too much. The up vector is way bigger than the down vector. So the up vector gets smaller and smaller, the down vector basically is constant, until the up vector equals the down vector, and the weight of the block is equal to the kx. Unless we made math there. Capiche? Here's the tricky part. I have been digging through exercises trying to figure out how to make this clear, and it's not easy. A lot of exercises will simply say, this equals it. They won't say, what is it when it returns? Or they'll say, what is the they'll say, okay, they will say, what is the maximum stretch of the spring? The maximum stretch of the spring is the big number, where mgh equals 1 fkx squared. So it should make a square. Okay. And then the equilibrium stretch where it ends up is the little number. Yes?
I'm just confused on when to use which formula.
Yeah, exactly. Me too. That's what I was kind of talking about. It depends. It's okay. This is the most important. This one almost always.
Okay.
So they will say words like, "What is the maximum stretch?" That.
If it's like a moving mass, it's that. But if it's just like a stationary and just put something on it, it's the other.
Yes. And I know this is kind of my white whale. I've been trying to figure out, like, going through all the exercises and like, okay, is it asking for that one or that one? Is it asking for this one or this one? This is just one of the things we're going to have to work out. Cool. It's usually this one.
So it's
Alright.
moving,
Now this one's also kind of fun too. Let's do it again. Only in this time, let's slide a block across a frictionless surface onto a horizontal spring. And this time we don't have gravity, but we do have a speed. I need some more dihydrogen peroxide. All right. So what do we do with a speed?
one
I'm gonna do it over there.
Not that useful.
So if we have a speed, then we have a kinetic energy. So in this case, the kinetic energy of the block rams into the spring. So we have 1/2 mx mv.
Yeah.
It's like, what the- 1/2 mv squared equals 1/2 kx squared. Right? M is still a 2 kilogram block, and now it's moving at 3 meters per second. So square it. So we got 18 joules of energy.
Wait, why is it not 9?
Because you gotta put.
You have
one
one,
Oh,
you
one
have
half.
two.
Yeah,
You can cancel the 1/2 step.
right. The whole thing was getting buggered on me. 9.0 joules equals 1/2 times 200 times x squared. So that's 100. So this 0.09 equals x squared. You said how much?
0.3.
0.3? Sounds good. Meters. So if the block slid into it horizontally, it would compress 0.30 meters.
But when it's settled, they just go back.
It's going to go back. And how much is it going to go back?
A lot. Infinite.
The same amount.
All the way, exactly. All the way. Because if we treat springs as ideal, and again, just like chemistry with gases, we treat springs like ideal, then it's going to get pushed back, and then it's going to push back against the block. It's going to send the block back at 3 meters per second, and the spring is going to return to its original position.
So it's just gonna go infinite because
It's not infinite, it's just it'll go back to a,
If you had another spring on the other side.
it's going to go back, yeah, it'll just keep going back and forth. Yeah, so it'll return back to its equilibrium position.
yeah,
If there's no friction and stuff.
Yeah, if there's no friction in the spring, which of course springs have a lot of friction, but you know, it'll go boing, then launch it back and come back right back to where it was. All right, how are we doing with this whole spring thing?
Does that not make sense?
It doesn't.
I
Can we discuss it some more?
No, I understand the equation in that part. Why doesn't the block just go
Oh, if
Well, it
distance?
would.
Yeah.
Because
It would because
Oh,
there's no
yes.
friction.
Yeah.
But the block is going to go boing, pew, and the spring is going to return back to its original position. Boing, squish, back to. So resisting potential energy, resisting only weight. Potential energy. Where this spring came from? How do you recognize it? Okay, anyway. So we'll move forward?
Yeah.
All right. Machines. This could be its own unit. Hell, this could be its own year, some machines. So we just kind of briefly hit some machines, and you don't have to memorize them, but there are 6 simple machines: a lever, a pulley, a wheel axle, which is a combination of a lever and a pulley,
Right. Awesome.
an inclined plane, a wedge, and a screw, which is a combination of an inclined plane and a wedge.
Yeah.
So this whole 6 simple machines is kind of like the 5 senses. You know that Aristotle said man observes his environment with 5 senses. And we know that's just way too simplified. Same thing, way too simplified, but it's been in textbooks for 50 years. So here it is.
There's really 4 plus 2.
Yes, there are 4 mechanical machines, but they all do the same thing. A simple mechanical machine changes the direction or amount of force. That's what makes it a simple machine. The simplest thing is a pulley. A single pulley only changes the direction of force. A lever changes the direction and the magnitude of force. We know the inclined plane changes direction and magnitude of force. Wedge, same thing. Screw, same thing. A wheel axle, again, a combination between a pulley and a lever, changes the direction and the magnitude of force. This is how your bicycle works. The reason you change gears is you can change the ratio of force you have to apply. Okay. Again, don't have to memorize it. But what is important is the formula. Here's the thing. If I go to Quentin's dad and I say, I need to jack up my car, he's going to give me a jack. There's a big bar. It's basically, if you've never seen a lever jack, there's a bar, and then that bar pushes up against another bar with a little thing that locks it in. So if I push down this part comes up, and it keeps locking it, brings it up and locks it, brings it up and locks it, brings it up and locks it. So if I take my bar and I go down 1 meter down, and the lift only goes up a centimeter, 100 centimeters, centimeter. That means I had to go 100 times further than the jack. But the trade-off is the jack will apply 100 times the force. Because I can't lift a 3,000 kilogram car. But if I apply only 30 kilograms, I can do that. Or sorry, 30 newtons. I can't lift I can't lift a 30,000 Newton car by myself. But I can apply 300 newtons several times. And that's how a machine works. They have an input force and an output force. And ideally, the effort force, which is the input force, multiplied by the effort distance equals the output force multiplied by the output distance. If there's no friction, which of course there is all the time, but we're going to pretend it doesn't exist. So the FEDE equals FRPR. Yeah, Feedy Fetter. Assuming that there is no work or no energy lost to friction. Of course, we know there is always energy lost to friction, but that's how it works. So I apply 1/100th the force, but I have to apply it 100 times as far. The machine applies 100 times the force, but applies it 1/100th as far. Make sense? By the way, your joints do this too. If we talk more about the different types of machines, there's different classes of levers, depending on what God decided you needed to do. So you have levers like your elbow where it pulls back. Can anyone basically lift themselves this way with their single elbow?
What?
Can you basically, I know you can do a push-up, but imagine if you could lift your mass this way.
Oh.
Yeah, probably not. Because your elbow, your muscle is pulling backwards on your elbow back here. Your elbow is not designed for strength. Your elbow is designed for speed. So you can swing your axe or stab the tiger with your spear. So your elbow is designed for speed. But you know what muscle is really good for strength?
Calves.
Your calves. Your calves are crazy good at moving a large force, but they're not very fast. You got to use your entire leg to jump. You can't just jump on your toe.
I think I could.
Without moving your knee?
Yeah.
Okay, give it a try.
I feel like
Can you leap with your knee locked? Just on your toes. With your knee totally locked. Okay. Yeah. Not very effective, but it does.
Well, I got that. Sure.
Yeah. So some levers are good for speed, and some levers are good for strength. And again, if you want more information about that, YouTube is a great place.
I got that.
Now, there's two types of mechanical advantage.
I just do it with me.
The mechanical advantage of a machine is based upon how much force it multiplies. So it's just the force the machine does divided by the force you do. If I do 30 newtons and the machine does 30,000 or 3,000 newtons, then I have a mechanical advantage of 100. It's really hard to pick up a dresser and set it into a moving truck. So I would have to be like, okay, this dresser is 50 kilograms, 500 newtons, and lift it up all 500 newtons. Or I could push it up a ramp. I would apply less force over a longer distance. Mechanical advantage. What mechanical advantage does not do is take into account friction, because there would be a bunch of frictional terms in here. So that allows, so you're going to need the ideal mechanical advantage, because distance is just distance. So if you have friction involved, then your ideal mechanical advantage is what you use that says this is the max. For instance, my going up into the U-Haul, putting the thing in the U-Haul, the distance, if I have to go 20 meters, if I have to go 10 meters instead of 1 meter, my mechanical advantage is 10. So I go 10 meters up the ramp instead of 1 meter into the truck, my mechanical advantage is 10. Yeah? But maybe I have to push 12 newtons instead of 100 newtons because there's friction involved. Mechanical advantage has to deal with the eventual friction. Ideal mechanical advantage doesn't. It's like, well, my ramp has a mechanical advantage or an ideal mechanical advantage of 100, but because there's friction, it only has a real mechanical advantage of 83. Make sense? I think we are just about done. Oh, yeah, this is what I was talking about. Okay, if you have a mechanical advantage larger than 1, that means the machine does more force over a smaller distance. If your mechanical advantage is less than 1, that means the machine is doing less force over a longer distance. You know, it's a really good really good machine with a much, much smaller mechanical advantage. Fishing rod. So like, zing! You could just chuck. Imagine how fast the lure is going. You could way faster than you could throw it because you got that big long bar. Same thing with the chuck it from your dog ball.
Yeah.
Yeah. So it's like you can get that thing going. Just like
Okay.
throw that way further.
Oh,
Get up to some major speed.
Yeah.
Because that bar gives you a very, very low mechanical advantage. Okay, and then an ideal mechanical advantage work in equals work out, so that applies. Okay. Again, in an ideal machine, work out equals work out. Okay. There's this neat trick that we're going to investigate with pulleys. And there's a video I need you to watch called Snatch Blocks. It's by Smarter Every Day. And there's a cool trick when you're using pulleys. I'm going to set up my pulley system here. Not today, maybe today. The number of moving rope segments is the ideal mechanical advantage. So if you have a pulley, I'm sorry, I should have set it up. It's in the back. If you have an ideal mechanical advantage, imagine there's a pulley there's a weight going over a pulley and I'm pulling. If I pull down a meter, the block goes up a meter. That's a mechanical advantage of 1. But if there's 2 links, there's a pulley here and a pulley here, and the pulley moves up, when I pull down 1 meter, it only goes half a meter. That's a mechanical advantage of 2. And if I have 4 pulleys moving 4 rope segments, if I pull down a meter, the mass only goes up a quarter of a meter. That's a mechanical advantage of 4. And that's the lab we're going to be doing tomorrow. I think tomorrow.
Probably.
I think it depends on if you go easier. Oh, no, ramps. Ramps are tomorrow, and then snatch blocks are Friday. So Friday we're going to play with the pulleys. Tomorrow we're going to talk about ramps. So ramps tomorrow, pulleys on Friday.
We should we should get that little scooter thing that we saw on, and we should have someone pull it up.
With a snatch block.
Yeah.
Okay. The efficiency of a machine is quite simply the work it gives out divided by the work it gives in. Again, taking into account friction forces. If I have to put in 1,000 joules, but I only get out 900 joules, it's 90% efficient. Pretty simple, I hope. What is the most efficient transportation machine ever invented? Modern bicycle. Yeah, it's crazy efficient. You know what the least efficient machine is?
Something like us.
Us.
Oh,
Our efficiency is extremely low. But bicycles are crazy. They're like in the upper 90s. We're like in the lower 20s. We're like cars. We burn a lot of fuel. Okay. Yeah, let's go with this. A pulley rope segments with 6 moving rope segments has a mechanical advantage of 6. What is the mechanical advantage system with 2 moving rope segments? 2. Okay. Because in this machine, there's 6 moving rope segments, but that means the 25 will lift 150, but it'll only go 1/6 as far. If the force required to lift a block M at a constant velocity of 65 newtons, what is the weight of the block? It's not a trick question.
60.
If the force required to lift a block at a constant velocity is 65 newtons, what is the weight of the block? 65 newtons. It's not a trick question. You're like, it's gotta be a trick. Oh, it's not a trick question. So if the weight of the block is 65 newtons, what's the mass of the block? 6.5 kilograms. So for every 50 centimeters or half a meter, the hand moves, how much does the block move?
70 centimeters.
Nope.
Oh, are you talking about that one?
Oh,
Well, we can talk about this one, but we're pretty much talking about this
I
one.
thought you were talking about.
Oh.
Yeah,
5
because
centimeters.
yeah, 25, because it's got 2 moving rope segments. So it has a mechanical advantage of 2. Yeah, again, the pictures, I still haven't figured out why Office throws this animation out the window every time it upgrades a version. But anyway, yeah, so if the hand moves 50 centimeters, the block with 2 moving rope segments moves 25 centimeters. And therefore, if you're moving 25 centimeters, 0.25 meters, and you're lifting 65 newtons, what's the work?
65 times 25.
1/4 of 65, 17?
Yeah.
Is that right? About 17?
16.25.
16.25. Okay. Does that make sense? Not hard math. Okay. Questions? All right. Then I'm done talking. We're compressed springs with machines. Yeah, cool. So tomorrow and Friday we're gonna do look at simple machines with ramps, like the U-Haul ramp, and then Friday and Monday we're gonna do the same thing with pulleys. I can't remember. I can't believe I'm so embarrassed I didn't set up my pulley system. I think I'll set it up today. All right, questions? Bye, Keone. I hope you enjoyed the video. He's probably watching right now, right?